do this. What questions y'all got? Dave, okay, yeah, so that one had a little bite to it. Yeah, so basically speaking, a hot tub has two shells. Something like this. Base radius is 4. The top radius is 8. Height is also 4, for how deep it is. Okay, so the empty tub is filled with water. So water coming out here at a constant rate. So you notice the water level of the tub is rising. At 6 inches a minute. So 3 inches. And when water is 6 inches. How long is it going to take to build? And so the things that the volume is frustrating, something like this. Small radiuses R, radius capital R, is H. The volume of this, 1/3 pi H. So that's kind of what you can get. Now, before we get into this too much, what's one hazard we have to look out for? Might burn you on the. I didn't write it up here, but the problem, what units are these all in? Feet. So let me be a little bit careful. Let me make kind of a silent here as we go along. Let's recount this before I forget. How about this? 1/4 foot. When the water is a 1/2 foot deep. Right, and that way I'll know. Let's make sure that I remember that. So, okay, so now let's draw a picture to help us out. As this hot tub is filling up, fills up with water. And that's going to be 4. This is H. That's how deep it is. And this is we'll call this R. Now, as this problem is progressing, the 4 is not changing right on the bottom. That's always there. but would everybody agree that the H is getting bigger and the R is getting bigger as you fill this up with water? Okay. So what is the volume of the water in? Oh, right, because 3 inches is 1/4 of a foot. Right, and 6 inches is a half. Right, and if you ever, so 4 6. See, I want to cancel inches and get feet. You know how many inches in 1 foot? Sure. So that's essentially one, right? 1 foot is 12 inches. And so you cancel the inches, and I'm looking at 3/12 of a foot, which is one. Okay. Okay. So what's the volume of the water in the hot cup? Well, it's changing. It involves both R and H. So let's see, rip off our formula. Here, the role of H is being played by H, and the role of R is being played by R. What's the role of little r being played by? 4. So slap a 4 for little r in this, and you get volumes. This is 1/3 H. Well, R squared plus 4R plus 60. Now let's look at the problem again. The water level is rising. So according to my figure, what is this telling us? Water level is rising. What is that? The H is deep. Right? The information is given to me about H. That's water level is rising. And the H was what? 1/4 foot per minute. When what? Right. So in people in this picture here, when H is right. That's how long it took. Somebody, so this is a little bit different. You got to figure out how we figure out how long it's built up. Give you volume and stuff. And so what we write this down. Okay, so we need the volume. All I have to do is use some formula. 1/3 for my full hot tub, the height is 4. And what do I have? R squared, so it's 8 squared plus 8 times 4 plus 4. So that's going to be 16, 80, 112, 4 is 448. You said find volume tough, and now what are you gonna do? What other piece of information do you need? That's exactly right, because we said in the problem that, I didn't write the complete problem down here, we said the problem that it would be put in constant rate. I'll just call it K, because I don't know what the answer is. This is in cubic feet. Minute. Okay. Explain to me why, if I can find those two things, I've already found one of them, but I can solve my problem. What do I do? Well, right, I mean, what you would expect is it looks like the water level rises quicker when you're smaller. But as it gets up, the water level will rise slower. But see, we don't need to get that complicated. All we need to know is the total volume of the tub. And remember, it's being filled at a constant rate. If I divide this number by this number, what will the units be? It'll be minutes. So this is the total volume of the tub. This is the rate at which it's being filled. If you take this number and divide by whatever this is, I'll get my answer. It'll be in minutes. So really, it boils down to this big question is finding this. So this looks like calculus. There's only one problem though, and that is when I take the derivative of this, I'm going to have some dHdt's. That's no problem. But I'm going to have some dRdt's too. Right? This is the trickiest part of the problem, and it doesn't really have much to do with calculus. It's really more like geometry. What do we have to do here to tackle this problem? Is we need to find H and R in terms of each other. Right? Here's how to find. So what I want to do, my goal is this thing involves two variables, H and R. I'd really like to get it to involve only H, right? Because I've got information on H. I don't have any information on R. Right? So I need some way to relate, I need to relate H and R. Yeah, it's a big thing. So let me start you off. Here's the radius at the top of the hot tub. Black. It's water. I'm just dying to use similar triangles, right? But I ain't got no triangles, right? And forget triangles. What's the cure for this? If you think about mathematics, it's something that you use, not something that uses you. All that X. All that. And by the way, can somebody remind me what's this distance here? No, I raised the original hot tub. Yeah, this was 4. Remember, because the whole hot tub was 4 deep. Now, my goal is I'm trying to get H and R related to each other. So let me try this. I'm going to try to find X first. X is to 4. So I'm saying this triangle, this imaginary triangle I extended below, X is to 4 as what? this is to this, as the whole side is to A. Do I agree with you? This here to here is to this, as the whole side is to this. Everybody okay with it? Now the whole side's A. What's this side right here?
Just X.
It's just X plus 4. Right? Now that's X and that's another 4. And if you work this out, this is 8X, it's 4X plus 16, or 4X equals 16. Four X equals 16, so that's. Okay, any questions? I'm just, this allows me to get R. So now, notice this intermediate triangle here is similar to this whole thing. Now I know X is 4. Do I agree? And so, looking at this big, look at the middle triangle now. R is to H plus 4 as as the R is to 8 plus 4 as 8 is to 8.
You just explain how X part of what R over H plus.
So this triangle here is similar to the entire triangle. So R is to this side, which is H plus 4. Is equal to the entire side, the entire side. That's 8 is 4 and 4 is 8. So R H plus 4. I'm not trying to play this here. So, let's see what we got here. R squared, it's H plus 4 squared, plus 4, H plus 4, plus 16. Um, Right. You know, here's kind of the gut check on this too. This equation R plus 4. think about this case, what happens when the water is 0 H? Right, so in this case, H is 0, right? And what is the radius R? It's 4. When you plug in 0, 4. What happens all the way up here? When H is all the way up here, that means that H is 4, and this says R is 4 plus 4. So it makes sense that this works, right? It works to do it. Right, okay? So what have I done here? I've used this equation here, and everywhere I see an R, I put in an H, because I've got everything in terms of H. Let me clean this up a little bit. This is H squared plus 8H plus 16 plus 4H plus 16 plus 16. This is H squared plus 12H plus 48. But volume is 1/3 times H cubed plus 12H squared plus 48H. Now, remember, we see VDT. Derivative of this, 1/3 pi is a constant, so it comes along with the right. This is 3H squared DHT plus 24H DHT plus 48 DH. Does everybody understand the derivative? So let's plug in. What was H? This is 1/2. And the HDT, 1/4. So I'm going to get DT 1/3 pi. So that's going to be 3H squared is 1/4. So that's going to be 3/4 times 4 is 3/16. This is 24 times H, which is 12 times a 4, 1 plus 3. And this is 48 times 4, which is 12. Okay, so this comes to, or let's see, I guess this is, that is 15 times 16. So I get 243 from 48 pi. And that should be cubic feet. And so, to answer the question, the total volume, which is 448 over 3 pi cubic feet, divided by 243 over 48 pi cubic feet a minute, and you'll get something in minutes. So that's going to be 448 over 243 times 60 minutes. Whatever that turns out to be, and I think that's probably, that's just a little bit less, that's roughly a half hour. Right, so that's a little bit less. Does everybody understand all of this one was decidedly the hardest one on the quiz, and you should thank me for putting me on the quiz, because I took it off the test and said, nah, that's put on the quiz. Does everybody understand all the procedure? This is, if you master this one, I think you've got a pretty good understanding. Okay. Other questions? Did you think the other ones were like easier, more chewable? Anybody want to see any of the other ones? Right, the one about the sand being done. Okay, so the problem says you got sand being dumped off of some conveyor or something, or out of some tube and a conical pile. So you got the sand being dumped out of this industrial strength sand pipe, and so it's like, have any of you ever watched like a, it's like an hourglass, right? You see what happens if you don't jiggle the hourglass, right? The sand always builds up in kind of a little conical pile, and if it gets too tall, it kind of breaks down a little bit. So we're assuming that the course is sand, I believe it says in the problem, guarantees that the radius and the height are always equal. So I gave you this general formula here. The volume of the cone is 1/3 pi height r squared. How many of you have seen this before? Volume of the cone is 1/3. Really, what it's saying is 1/3 the height times the base. Because actually, let me put this way. So it's clear. 1/3 the base, which is the circle power squared times the height. How many of you have seen that? Well, here's the cool thing about it. I remember when I first saw this one, saying things, guessing it's about 1/3. No, that's exact. And when you get further into like 1080, you can derive this from scratch. But for now, you can just take this as manna from heaven. Now, I've got this stuff, it's making this pile of sand. Can assume radius equals height. So the course this is the same, so it plays out that way. So what's my new improved formula for volume? This is much better. Right, you can replace H with R or R with H. I'm gonna replace R with H, it really doesn't matter. But I prefer to do that only because in the problem, here's what it says. The pile of sand is increasing at 6 inches per second when the height of the pile is 10 feet. So everything's in terms of height. They tell me how the height is changing, when it's so high. So I'm gonna put this, instead of selecting the term H and R, I select the term R and A. It's 6 in one, half dozen the other, but this saves a step. So what was that piece of information? Height pile is increased at 6 inches. Height of the pile increased 6 inches per second when the height is 10 feet. Okay, so do you see a problem that maybe you've got to be careful about? You've got always got we've got a unit that's matched, right? So let's do this. Everything else seems to be complete. Instead of 6 inches per second, say a half a foot per second. Okay, so interpret that. So here's what my pile looks like. Radius and height are as one. So 6 inches per second, what is that? H T 1/2 foot per second. Now this is positive because of course the pile is increasing, the height is getting bigger. When H is equal to good. So, and the quest, what is it? What do you think? It says at what rate is the sand being dumped on the platform? So somebody, what is the procedure? This is at what rate is the sand being dumped on the platform? What are we looking for? Exactly, DBT. There's a good gut check for this. Think about the way that question is asked and what your unit should be. At what rate is the sand being done? I would expect something like cubic feet per second, something like that. So there should be a change in the volume with respect to time. Cubic feet per second. Right. Want this. Now, I did say in the problem that this is a constant rate. So if it's a constant rate, the pile grows very fast at first and slows down, right? I mean, when this pile is a mile high, it's going to be growing very, very slowly. But this information should tell us what this constant rate is. So let's take and let's be clear. Everybody okay with that? I get that? This is what we see, and I think all we're going to have to do is just play with the numbers. So let's give that a shot. Ah, the 3 came down and killed it. 10 squared, and what was the case? This should be I get 55. Yeah, it's like so basically bigger than a 5 by 5 and 5 2% 37. So it's guessing up there by our standards, I guess. Okay, any questions? Okay, other questions? Anything goes. Do you want me to do some of the old problems? Or you want me to make something up? So,
Yeah, it makes.
okay. So. This. Okay, this one actually combines several things. Let's see. DDXs. Okay. What's the first thing you do? Sign some blob, and what's the derivative? Sign blob. Sure. Now, what's the derivative of blob? Right. I'm gonna come back. Check out the other side. What's the derivative of e to the blob? There you go. And what's the derivative of blob? Again, I don't know. So. We're gonna come back to that. Let's take a little aside and see if we can figure out. Dude, goodness gracious, how do I do that? Yeah, I mean, that's gonna fit. Yeah. You recognize that what I have is variable X and variable X function, so there's lots of it. So for convenience, I'm gonna call it something. And what I'm looking for is, well, if I can be careful here, find X. Correct? If I call this Z, I'm looking for DDX of this thing, DDX. This form makes it sort of notationally convenient for me. I'm gonna do exactly what you prescribed here. Let's throw a log at this, so this isn't as bad. Right? Okay. Now let's ddx this. That's what we want. And I have 1 over z dx, or z prime, is, take the derivative of this. It's this times the derivative of this, plus dy dx times log x. So I've got my first answer. Z dx, you see, times its mass. And what is z? It is x to the y. And what is the mass? It's y over x plus y prime log x. Y x, y prime log x. So let me place this in bits. First bit is cosine x and y times ddx of x to the y, which we figured out is x to the y times y over x plus y prime log x. So we're sort of halfway through. Let me give you guys a chance to catch up. Is anybody with me on that? Don't be shy. This review session for you guys. So if I do anything that's too fast to lose, let me know.
On the test form, so when you write dy dx in the equation, it's the same as writing y part, right? You know,
Right. So here's the reason why I'm making a distinction. Y prime means the derivative of y, but with respect to one variable, you've got 3 letters here. I wanted to make it clear that I'm taking the derivative with respect to x, right? So, because remember what we do here is when we take the derivative of this thing, it's y times the derivative of log x, which is 1 over x. And then it is the derivative of y, which is not 1 necessarily, it's dy dx times log x. So I'm just being careful with the notation. The thing in the bottom of ddx, that tells you what variable I'm taking the derivative. Is everybody okay with this part of this? Okay, so let's look at the other thing, which actually should be the same, or not same, but very similar. We need d dx this time, y to the x. So this should be some. Someone did the same thing again. I'm going to let some other letter. I'm going to let t equal y dx, and I'm going to find t dx. Same before. I've got that same log problem here. I'm going to try to solve my little log problem in the same way. When I take the log of y to the x, that allows me to bring down the exponent of x. And now ddx. One over t times t dx is equal to derivative of x is 1 plus x times the derivative of log y, 1 over y dx. So I get something similar here. I get t dx is t times mass. And this time the mass looks very similar. What was t? T was y dx. And mass is log y plus x over y. And so the other side becomes e y x times y the x log y plus x over y. Right, okay. Now, I guess I did say if you're fine, y prime. So now I've got to go through the algorithm roles, since that's what I said, problem. So what do I get here? I get cosine x y times x y over x plus y prime log x cosine x y. That's what I get when I multiply this to these. But x y multiplied cosine y log x. This I get e to the y to the x, y to the x log y plus e to the y to the x, y to the x, x over y on prime. Now, put everything, and it doesn't matter which side you use, but put everything with a y prime in it on one side, everything with no y prime in it on another side. So I'm going to get cosine x to the y times x to the y, that's y over x, minus y of x, y of x. Log y. That's it's equal to e to the y of x, y to the x over y, solve for y prime, minus cosine x y, x y, log x. So when I file y prime implicitly, not surprisingly involved both x and y. It's cosine x y, x y, y over x, minus e to the y of x, y of the x, log y over e, y of the x, y of the x over y, minus cosine x y, x y, log x. By the way, please do not obsess about trying to simplify anything. For example, you can cancel this x with y. This right here, you can call this x to the y minus 1 power. Forget about all that. Just do the calculus. Notice. By the way, how can you verify that 0, 1 isn't back on that curve? Just plug in and see if it balances the equation. When x is 0, notice that the second term on the left side and the second term on the right side are gone. When x is 0, and you get y cubed equals y. If y equals 1, that balances it, and if y equals negative. Notice that whatever this curve looks like, it isn't a function because this is a pretty shoddy drawing of the curve, but I do know it goes through those 2 points. So for sure it fails the vertical line test, right? Even though I've only put 2 points. Okay, so let's get the derivative. Make sure that you really do. Okay, you know what? I can solve this, I'm terrible. I think this strategy is this. Plug in everywhere I see an X, makes the term disappear. So, and plug in 1 here, so it's going 3y prime. There's an X there, so that's gone. There's an X there, so that's gone. Y prime, there's an X there, that's gone. So 2y prime is 0, so y prime is 0. With the tangent line, y equals 1. Means formally, careful, it's y minus 1 is 0 times x minus 0. Right? And this gives y equals 1. I think we can do something similar to the other point. Where are you okay now?
Yeah.
For 0 minus 1. And I get, well, notice when I plug in minus 1 here, I still get 3. 0, 0, a y prime, 0. So for the tangent in 0. And actually, that gives you a little clue about, I mean, there's a lot more to figure out, but however this thing hits the point, slope of this tangent, 0. So maybe it's this, maybe it's this, who knows? We have to do it work. Okay, other questions? What's that? Sure. We want to take to incorporate that in. Oh, I've got. How about one's a little bit about practical? This is the kind of thing that helps you get to, like, problems. How many of you have ever been to an art museum? Seen a work of art that you particularly like? What do? Go up close? See, if I go up and look at the artwork like this? No, too close. And you probably don't go like into the next county and try to look at it either, right? So have you ever done this? Like you see something you like, you admire, and maybe back up, try to adjust a little bit? Well, there's a reason for that. So you're looking at a painting. Painting is a high page. Box at your eye level, but hanging high on the wall. So the question you might ask yourself is, how far away do I stand from that painting to get the optimal view? Because notice, if you stand really close, you don't very good vision. And if you stand far away, then the angle is very, very small. Right? So here's what I'm going to do. Distance X. Find theta X, where theta is so the angle drop all takes in so straight. Okay, so here's X, the distance at which you chose to stand at the wall. You can vary, you can go out. Can somebody, so let's find the theta X. Anybody find a function that balances X to theta? Yeah, that's right. That's right. So if I were to say tangent theta, what would you say? So there's many ways to do this, but I think sometimes I like to take fractions out of the picture. But h be the tangent of theta. Derivative of h is 0. Right, because h is the height of, it's just the height of the beam. That's fixed, it never changes. That h is always the same, so its derivative is 0. This is the good old product. So the first thing we get is the derivative of x, which is 1, tangent theta, plus x comes the derivative of tangent theta. So the first thing you come to is tangent. What's the derivative of tangent? I'm not done. Theta x. So I can actually solve this. So what I get is theta dx is equal to minus tangent theta over x secant squared x. I'm sorry, x secant squared theta. By the way, this is probably not very satisfying. Because I'm going to get to some inverse rate stuff later too, but I think this might help. This is unsatisfying because I have this, I have this simplicity. Okay. What about, you know what? This formula involves both x and theta, which is obnoxious, right? Wouldn't it be easier if the only thing that I need to know is the parameter of x that I extend there? Can we do that here? This might help. Oh, so it looks to me like theta dx is minus tangent theta over x tangent squared theta. But does this help? I love to get rid of the theta since it's on there. It's gotta help. Here. And theta is h over x, right? So x h squared x squared. So I reckon that I could multiply both top and bottom by x squared. Multiply top and bottom by x squared. Minus hx on the top. On the bottom, h squared. That's x. X increases. Any less bigger. Okay, any questions? Rich, let me try to address, and you can tell me if it's satisfactory. So I can do more. So what if I actually do this? Somebody remind me, what is the derivative inverse tangent of log?
Is one of the log squared.
Agree. Okay. So let's apply that. First thing I come to is the inverse tangent of log. So that's 1 over log squared. 1. Am I done? What do I got to what do I got to do now? Okay, and what do I come to first? The derivative sine of log is still not done. Gonna multiply that by the variable that's inside. Absolutely, yeah. In fact, a good rule of thumb is don't ever simplify something unless there's something in it for you. Right, so for example, if the question had gone on to say, where's the derivative 0 or something like this, and I have no idea what GT. But if it said something like find where this is 0 or something like that, then you might simplify it or something here. Just don't mess with it. Move on with your life. Okay. Other questions? Sure, of course. Got it. X is equal to x cubed is 2x. Sine pi x plus as. So you can just make this as given, although I'll discuss this. If we denote this in our function, we're going to need the derivative of this function later. So, yes, help me out. What is the derivative of this function?
I found this very good.
So that's gonna be cosine block for the derivative block. So this has an inversion. It's given. So notice we will find and here's the big result we had last time before. Going over that A, where F A. So let me explain this. A3 graph F. So 3A, the reverse of it is so really the part of this is finding this is an easy problem if you know what A is. So I want you guys to consider this for a minute, see if you can tell me for what value of A can I plug in for X? For what value of X can I plug in for the function of X? And it's going to barf out at 3. 0. Very good. And I don't know any other way to tell you than try some simple things with some common sense to look at this. Because I set this up for if you plug in 0, it's 0 plus 0 plus 0 plus 3. So I found a point, namely A is 0. When I plug it in, I get 3. And I know that if this function is 1 to 1, that's the only solution. So in our case, this is 1 over f prime 0. And let's just hope we do 0 denominator. So when I'm plugging 0, I get 0 plus 2 plus pi cosine. Oh, so that's going to be cosine 0 is 1. So I get over 2 plus 1. Tricky part of it. So, I mean, you have to remember the formula. The derivative of the inverse of the thing is 1 over the derivative of the original function at the corresponding point. A3 is on the graph, 3A is on the graph. The inverse. Yeah, your book uses this notation. And I just say, look, because I just really just okay. Okay. Other question. Oh, like yeah. So let me see if I've got it right. about that for a little bit. This is the kind of thing you need. Can everybody read when I wrote? The first thing is to take this piece of garbage, rewrite it in workable form. Oh, and you know what? I see, does anybody see a Lego shortcut this? Actually, you know what? I'm gonna take a shortcut out. I'm gonna take the problems. Sure. Otherwise, I can shortcut it out. It might take away the spirit of what you need to do. So let's think about this from a calculator perspective. If I were to put this going to be calculated, I would do that. X to the X plus 3 to the fourth 3. Then I would add sine of X squared to it. And once I was done doing that, I took the cube root of that in the bottom. And then I would add X to it. And I will take the square root of the whole shebang. Right. Okay, so let's and actually I'll show you what I do when we get this stuff. What's the first thing that what's the first thing? Something to the 1/2. So it's gonna be 1/2 log. And there we go. First piece totally fine, right? Now I go inside the parentheses. There's orange stuff here. What I come to is that X plus a mess. Okay, let's do the square root of X. There you go. What's the derivative of the next piece? What's the next thing that I come to? Some block of 1/3. Now I'm done taking the derivative X. We're not doing the derivative, the rest of it. I mean, I'm not done taking the derivative of this. Just blob to the 1/3, because now I'm gonna go inside the parentheses, multiply by through what I find here. First piece, what do I come to first? Okay, it's derivative sine of blob and cosine blob. Am I done? Not plus, you gotta multiply by 2x. So there's that. So I've got this piece. What about this piece? That is log. And unfortunately, I'm not done taking the derivative of this. All right. I've got to go inside here. And multiply this thing by the derivative of what I find inside here. What's the derivative of x dx? Some of you may remember, but that is correct. Everybody agree with that? And I'm sort of done. Close my green. Close my double. This is the correct, albeit perhaps bit incomplete answer. It is 1/2 log minus 1/2. Whichever what's inside. 1 plus 1/3 log minus 2/3. Not done taking the derivative of this, but multiply by derivative of this. That's this, and now I'm not done taking the derivative of this. Everybody follow that. There's one final step to make this problem really most triumphant one, and that is here. So really, what I would do, I would say, like prime, and for this one, of course, then throw a log with it. So y is x to the x. Log y is x log x. Guess that. And it's y prime. This is 1 times log x. 1 times log x plus x. 1 over x. Split log x. 1. So y prime is y log x plus 1. X to the x. I will go x, x. Each of which is not rewriting this whole thing, but it is incumbent upon you to make it clear what pieces parts go to. So is that example clear? And was that what you were looking for? Yeah, that is actually some of the merits of calculus. We haven't even seen the big merits yet. Because do you remember the definition of the derivative? Remember doing all those problems? With the f of x plus h minus f of x over h, you take the limit, and you did that with the square root, you had to conjugate. You remember all those problems? Now, imagine for a second that somebody asked you to do that with this, right? You tell them to go jump in the lake, right? It's amazing that just from that, we were able to get all these formulas that make, there's no way in this God's green earth ever want to do this. It's just that on top of it. Oh, you mean like when you get something complicated and you want to use a log to make it easier, right? So, for example, if I gave you something like, so you can tell me this, has everybody got what we need from the board? If I gave you something like, say, this. Suppose I gave you something like that, so it's a derivative, right? Right, the point is, you don't have to, right? I mean, this is doable, this is, I mean, there's some new stuff in there, inverse tangent, right? But for the most part, without the inverse tangent laws, you could have done this before you got this class. But nobody wants to, right? The quotient rule's awful, right? You square the bottom, and that's your easy. Bottom comes through the top, there's like a pi rule with three things in it, or a chain rule, minus top through the bottom, it's worse. So what makes this easier is the logs. Here's the thing about logs. They turn products into sums. And it's easier to take the derivative of x plus sine x than it is to take x times sine. Logs turns products into sums. They turn quotients into differences. And they allow you to bring powers down. And that's why you want to use them. So if you take the natural log of y, this is the natural log of the first guy plus 17 natural log of the second guy plus 5 halves natural log of the third guy. Now these all come off the bottom. So it's the natural log of this. Well, the natural log of E, that just cancels. Minus 7 halves natural log of x squared plus 3. That's x cubed. Minus natural log inverse tangent x squared plus 5. Minus 5 natural log cosine 5 natural log cosine log x. Okay, before I go any further, I have done no calculus. What I have done is stuff that in theory you could have done with pre-calculus. I've used properties of laws to break it up. And I did that fast to kind of make the point. I want to make sure you all understand where every bit of that came from. Log of this, log of this, log of this. Those are the three pluses. That's log this plus 17, bring it down, log of the second, 5 halves, and bring it down log of this. And subtracting the logs of these. The log of E is just back to this, so it's minus x squared plus x, minus 7 halves log of that, minus log inverse tangent. By the way, don't bring that minus 1 down, right? Because this doesn't mean tangent x to the minus 1 power. This means inverse tangent, something different. So that and minus 5 log cosine log. Everybody cool?
Yeah.
I mean tangent, so tangent x is minus 1 power, cotangent. Or you could bring the minus sign out and you're good to go. Minus log of tangent x. But this is the inverse tangent. Now let's ddx this. And I get 1 over y prime. And remember, y prime is what we see. right, the derivative of this. And this is, you may think this is gnarly, but it's so much easier to do it the other way. Derivative of log blob is 1 over blob. Which in this case, 1 over that. Times the derivative of what's inside, which is 1 over x squared plus 1. Times the derivative of what's inside, which is 2x. Everybody see how I worked that first derivative there? Derivative of log blob is 1 over blob. Derivative of log of inner blob is 1 over x squared plus 1. Derivative of that is 2x. Well, here's it. Next term, 17 on for the right, 1 over x cubed plus 4 times derivative of what's inside, which is 3x squared.
Just right there, 17.
Absolutely. I'm just separating this out and trying to emphasize what's going on. And in fact, we're going to do that in a later step. 5 halves, 1 over sine x times the derivative of sine x, which is cosine x, minus 2x minus 1, okay, minus 7 halves, 1 over x cubed plus 3 times 3x squared, minus 1 over inverse tangent x squared plus 5. Okay. Now times the derivative of what's inside. Derivative of inverse tangent blob is 1 over blob squared plus 1. Now the derivative of what's inside there is 2x. Finally, minus 5, 1 over cosine log x. The derivative of cosine of blob is minus sine log x. The derivative of log x is 1x. Okay, I want you all to look at that and make sure that you understand. Now, the worst one is inverse tangent. Everybody understand that? 1 over the inverse tangent blob. Derivative of inverse, then it's derivative of inverse tangent blob, which is 1 over blob squared plus 1. Derivative was inside. So I'm going to clean this up just a bit. Two x over x squared plus 1 log x squared plus 1 plus 51 x squared over x cubed plus 4 plus 5 halves of tangent x cosine of sine it is minus 2x minus 1 minus, that's going to be 21 halves of x squared over x cubed plus 3 minus 2x over inverse tangent x squared plus 5 x squared plus 5 squared plus 1. Make sure you put that in parentheses. Multiply. Finally, let's see, the minuses here should cancel. And again, I get cotangent plus 5 cotangent log x over x. And then just make clear to me this, it's this. So it's this whole thing multiplying this, and you're good to go. And although at this point in your life, this may not seem like a shortcut, I challenge you to do that without doing qualities involved. You will be weaving a tapestry of profanities very quickly. No, just write something on your paper, just in some way communicate to me, one human being to another, that you know that Y is supposed to be this thing. So that you got all the pieces, right? You've got all the Legos, I don't need you to reassemble them, don't wait for testing. In fact, so if you get nervous about such things, here's what to do. Once you get to this point, move on with your life, finish the test. If you got time, come back and clean it up. Polish it.
For the final step, would you still accept it if it was like second step or call out if we just took what you wrote out in the second line, put it down, that's yeah, that would be something.
Oh, so if you said, if you made clear that this bit is mess and this bit is why, I'm okay with that. As long, see, and actually, I really think the math classes that you all should get some kind of general education, communication, successfully do it, because math is something that a lot of people find difficult, a lot more so than you all do, and you need to be able, when you learn the math, to communicate with them. It's not effective. And so, communicate to me clearly, and I'll be good with it. Okay, other questions? I'm doing too fast. My bad. Right here, let's change it because it's sign of the coast. I'll just fix it on this other side. So that last one should be tangent to all things. I mean, you can count on some related rates problems. Oh, and so I coached you today. Remember how I said 3 points this, 3 points this, 3 points this, and then solve the problem. The related rates problem, the exams will probably be worth more, but I won't break it down like that, but I suggest you do. Right? So even if you can't finish the problem, if you're stuck, tell me what you know. But you remember the problem about the one about the hot tub, right? It would be good, even if you can't get it, to say, look, here's what I gotta do. I gotta figure out the volume of the stupid tub, and I've gotta find my ddt and divide that into the volume to get, tell me, you all are engineers, scientists, et cetera. Tell me what you know. Right? If you get an answer that doesn't make sense, I take a lot of sympathy in this. You get an answer that doesn't make sense, and you think it's wrong, Tell me why you think it doesn't make sense. This is a skill, I think, that you're gonna need, science engineer, is you're gonna have fancy things that you learn how to do all this kind of cool stuff. But you also need to be able to look at it again and say, this makes sense. It's ballpark, right? That's something as far as I can tell, hey, I'm doing that. So. Uh, I think if you look at the exam from last year, you can that way. The truth is, given the fact that we've got a 2-hour class period, I don't think that. Well, I think by the end of the period, you're gonna be done, right? I mean, and anything that you haven't taught, it's like, an extra 3 hours is gonna help. Right? So, they're about, so all my exams, my midterms, there's 4 of them. They'll all be worth 100 points on paper. And you automatically get another 10 points added on the top of that if you come to my office and chit chat with me after it's over. Because I want you to get a meeting with me after every exam, see where you're at and all this kind of thing. Oh, and by the way, nobody should drop this class without talking to the coach, right? Because, your grades probably may look low compared to the other things, but actually your grades are right. There's nobody here that's below the C. So anyway, and so at the end of the semester, I'm in value judgment on where they are. If you get 90 in my class, you can put sugar in my gas tank and key my car and you still get an A, right? Now, do you have to get a 90? Well, key my car maybe, but probably not, right? But we'll see. And as the semester goes on and I look at the data as it's coming in, I can give you a pretty intelligent guesstimate about what it is. But of course, like I said, the way to live your life is you have to live your life like, I'm gonna stick to that. If you want to know what your quiz average is, come and ask me, I can tell you, because there's no way you know what your quiz average. I know that you all have it, but I run the program. You can't possibly know what your quiz average is without knowing everybody else's, which so I can tell you, whoever is the #1 person in here right now. Quiz average. And Candy's can't tell you, but like I said, I tell you, you're done. So. Okay. Other questions? Well, that's good. I mean, the best thing for you to do is sit down and crack those problems up in the shape. Don't stay up till 3 in the morning doing it. Make sure that you guys get rested. And don't let the first one bother you. There should be a learning curve on the first one, especially that fast. But this is hard advice to follow, which is try to relax and have some fun with it. Just do your best. I've seen good things from all of you, so I've got good expectations.